Hello, my friend. Today we will once again explore and talk about the topic, why did time start going forward? Let's dive into it together with HaiAstro. A Roman bishop sits at the window of his episcopal home on the North African coast. It is late afternoon. He watches the sun sink toward the Mediterranean, and he watches the waves break along the shore, sand piling into disordered heaps. When the sun drops lower, it will be time to light the lamps if he wants to keep working. He is Augustine of Hippo, theologian, philosopher, and saint, famed for the millions of words that survived into the modern age. And as he stares at the golden light, he feels an ache that is almost childlike. He wants it to remain. He wants time to pause or even run backward. What would that look like? He imagines the sun rising from the horizon, not so different from the glory of a dawn. But everything else, everything human, would look wrong. The waves that crashed onto the beach would have to uncrash. Water droplets would rise toward one another, assembling into teetering heaps before retreating as one body back out to sea. It feels like a violation of the Lord's natural order, and Augustine recoils from the discomfort of it. But then his mind drifts to a darker image, one he cannot quite resist. What if he could witness time laid out ahead of him, moving forward inexorably from one moment to the next? The waves would keep crashing unceasingly, advancing on the bustling town until it reduced it to rubble and sand. His home, too, would become a heap, indistinguishable from the shore itself. As his quill drips ink onto parchment, Augustine's thoughts spiral further. He sees time as a force that advances and ruins all in its path, spreading a relentless chaos. The present world of man crumbles into meaningless piles. The thriving natural world decays into dust on the wind. And in the sky, stars wink out one by one until there is nothing left by which to measure passing moments. With nothing more for time to devour, would that finally be the end of the beast itself? What then is time, if not the march of disorder, the slow unmaking of God's structured universe into an eternal pile of sand? He shakes himself free of the waking dream and realizes it truly is darkening. With the last glimmers of sunset, he draws a slow breath and scratches out his final words for the day. What then is time? But if Augustine could have looked forward, if he could have seen into the minds of modern scholars, he would have discovered something unsettling. His dark imaginings were not merely poetic. They were, in a strange way, substantiated by the highest theoretical physics and cosmology. The hungry beast of time, powered by ever-growing entropy, is relentless, not because some demon delights in destruction, but because mathematics itself, cold and unarguable, grips the cosmos from its first moments to its last. Entropy, bound into the behavior of particles and energy, powers what we call the arrow of time. It pushes our experience forward into a future that feels unavoidable and at times disturbing, while the past remains forever out of reach. And this is where our story begins, because time is not just a feeling in the human mind, it's a physical feature of the universe. Yet we do something strange with it. We build clocks, we draw lines, we decide what counts as now, and we pretend those lines are real. Something like this happened about 1.5 millennia after Augustine struggled to define time. In the industrial English city of Manchester, in the early 19th century, people were preparing to manipulate it. Back then, clocks were calibrated against local sundials, which meant time could differ by as much as 30 minutes between the west and east coasts of England. That wasn't a problem when most people lived and died within a few miles of their birthplace. But the Industrial Revolution changed the rules. Railways spread like arteries across the country, and suddenly England needed a unified system. A difference of even a few minutes between London and another station could mean missed trains, confusion, even collisions on intersecting tracks. So for the first time in history, time itself would be changed. In January 1846, the residents of Manchester collectively traveled through time, jumping 13 minutes in an instant as the city's clocks were adjusted to match the standard time
set by the Royal Observatory in Greenwich, London.
For millennia, time had been measured by the sun, by shadows, by the sky. But this was the first time it had been standardized, forced into a single order by the demands of industry. And yet, if you think about it, this standard time is arbitrary. It's an imaginary structure built for busy lives. The sun still sets in Manchester 13 minutes later than in London, regardless of what the clocks insist. But those steam-powered locomotives did more than reorganize schedules. They opened our minds to the nature of time in an unexpected way. Because the engines that powered the Industrial Revolution were also heat engines, and heat, long before it became a symbol of comfort, became a clue to time itself. About 20 years before England surrendered to railway time, efforts to understand steam power led a French engineer and physicist, Sadi Carnot, to make a prophetic observation. Steam engines were being adopted across the rapidly industrializing world, bringing wealth to those who embraced them. Yet few people truly understood how they worked. That was Carnot's concern. In 1824, he wrote his influential reflections on the motive power of fire. His key observation, which seems obvious now, was that heat always flows from a warmer body to a colder one. That's why a fireplace warms a cold room, why ice melts in sunlight, why molten newborn planets cool in the vacuum of space. It is an irreversible process, and it is what provides the motive force in heat engines. In hindsight, Carnot was laying the foundation for what would become the second law of thermodynamics. Over the next century, that law evolved alongside our physics until we recognized something even deeper. Not just heat, but all systems tend to move in a direction that reduces their free energy. Today, we describe this one-way drift using a single word: entropy. Entropy is a mathematical measure of disorder, but more precisely, it measures how many different microscopic arrangements can produce the same macroscopic state. A functioning train locomotive is an exquisitely ordered structure. There are very few ways to arrange its components and still produce an engine that runs, so its entropy is low. But a heap of wreckage in a scrapyard may contain the same parts piled in disorder. There are countless ways to arrange scrap into a chaotic pile. That multiplicity of possibilities is why its entropy is high. And here is the rule that changes everything. Entropy tends to increase. A working locomotive left long enough will become wreckage. The chance that a pile of engine parts spontaneously assembles itself into a functioning train is not just small, it's effectively non-existent. Disorder is overwhelmingly more likely than order. When coal burns in an engine, it changes irreversibly from a structured lump of energy-rich carbon into ash, while its free energy is dissipated as heat into the boiler and the world. This tendency toward disorder is not just the reason steam engines work, it may be the basis of time itself. Because if everything around us is constantly drifting from order to disorder, that drift provides a way to distinguish one moment from the next. It gives time its direction. And one man watching the stars in Cambridge would eventually give that direction a name. It was just past dawn when Arthur Eddington began walking home through the streets of Cambridge. He'd spent the night peering up at the stars from the University Observatory, and his mind was still filled with wheeling points of light as he tried to make sense of their motions. Then, not far from the door to his apartment, he was pulled sharply out of his thoughts. A stern-faced woman stepped into his path and held out a white feather, soft down catching in the morning breeze. He knew better than to resist taking it. He smiled politely, stepped around her, and a few moments later, inside his home, he shook off his coat, hung his hat, and added the feather to the growing pile on his mantelpiece. It was 1917, and Eddington was a Quaker and a pacifist. In the eyes of society, that made him a coward. But Eddington was no coward in confronting the mysteries of the cosmos.
He became a world leader in gravity and relativity, and in 1928, he wrote an ambitious book that introduced ordinary readers to one of the most profound ideas in physics: entropy as a universal arrow. He asked us to imagine the increase of entropy as an arrow that points from order to disorder, from past to future. And in doing so, he helped define what we now call the arrow of time, the direction of time set by the directional growth of entropy. As time moves forward, systems become more disordered, and that irreversible change is how we experience time as moving. It's why cause precedes effect. It's why we remember yesterday but not tomorrow. Time travel, of course, has become one of the most beloved tropes in science fiction, precisely because it bends our minds with paradox.
But to travel backward in time, you would need to experience the universe in the unsettling improbability of decreasing entropy, of things spontaneously becoming more ordered. Waves would have to uncrash and retreat from the shore. Wreckage would have to self-assemble into engines. It feels not only unnatural, but fundamentally forbidden by the arrow of time that governs the universe and our own experience. Even if you imagine instantaneous travel backward, jumping to the past and then living forward again, something breaks. You can no longer define a consistent, universal arrow of time. The universe would contain contradictory directions, and physics hates contradictions. Now, the mathematics of relativity adds another layer of temptation. Theoretically, if you could travel faster than the speed of light, the intimate relationship between space and time suggests you could also move backward in time. But theory and reality are not the same. The speed of light is one of the most reliable constants we've ever discovered. As you approach it, Einstein's equations tell us your mass rises toward infinity while your length contracts toward zero. Surpass it, and you don't just bend physics, you shatter it. And there is a deeper problem. If you could outrun light and arrive before you departed, you fall into a causal loop, isolated from the normal universe where cause must precede effect. Stephen Hawking was so confident that reverse time travel is impossible that he held a party on June 28, 2009, and only sent the invitations the next day. The only way anyone could attend would be if they traveled backward in time. Nobody came. Hawking was left alone with 10 bottles of champagne and a quiet grin that said, "The universe agrees with me." Traveling forward in time is another matter. That's easy. We do it constantly, 1 second per second. And we can even do it faster. If you stray too close to a black hole, where gravity distorts space-time, time for you can slow relative to time far away. Skirt close to the event horizon of a rotating black hole about 8 times the mass of our sun, and you could move forward in time tens of thousands of times faster than your companions on Earth. In 1 second of your life, 17 Earth hours could pass. The arrow of time dictates direction, not speed. This is where time becomes even stranger. Most physical laws are symmetrical. Collisions between gas particles, for example, look almost identical whether played forward or backward. 2 particles bounce like steel balls, conserving energy and momentum. Gravity, too, behaves the same whether you observe it now or a million years ago. But the arrow of time seems to violate this symmetry. Entropy increases on large scales, and time flows forward. Yet the underlying microscopic laws don't obviously demand that. Reconciling these facts is one of the great unanswered problems in physics. Some have even suggested the very existence of time is an illusion, a consequence of our inability to perceive the universe in full detail. In the early 19th century, the French philosopher and physicist Pierre-Simon Laplace imagined a terrifying possibility: an omniscient intellect, a demon, who could know the precise position and momentum of every atom in the universe and calculate the future and past with perfect accuracy. If the laws of nature are symmetrical and deterministic, Laplace's demon seems plausible. But entropy and time suggest otherwise. The irreversibility created by energy dissipation and growing disorder makes rigid prediction impossible. And on the smallest scales, quantum mechanics enters like a wrecking ball. Quantum uncertainty means you cannot simultaneously know both the position and speed of even a single atom with perfect precision, let alone every atom in the cosmos. If you could, entropy would lose meaning. Disorder would be fully trackable.
In a sense, entropy would vanish, and with it, the arrow of time. But this still leaves the haunting question: why is time asymmetric in the first place? Modern scientists have suggested that our ability to define the arrow of time comes from our proximity to the Big Bang. Just as up and down only mean something near a planet's surface, perhaps past and future only mean something because we live relatively close, cosmologically speaking, to the beginning. If that's true, then the Big Bang must have been a moment of extreme conditions from which the universe is still unwinding nearly 14 billion years later. And if time is a winding down process, then entropy is the winding itself. To understand that, we need to meet the man who made entropy a language of atoms.
Ludwig Boltzmann never stayed in one place for long. In the late 19th century, he moved from post to post: Vienna, Graz, Heidelberg, Berlin, restless as if his own life mirrored the atoms he studied, always moving, never settling, charged with unpredictable energy. His personality swung violently from exalted joy to suicidal depression, but his turbulence did not dull his scientific brilliance. He was a pioneer ahead of his time, developing an entirely new field, statistical mechanics. With it, he built a framework to understand the growth of entropy for the first time in microscopic terms. He imagined colliding particles as balls on a billiard table. The physics of any one collision is predictable if you know the speed and angle, if the usual laws apply. But the more collisions occur, one after another, the more disordered the table becomes. It becomes increasingly unlikely that further collisions will accidentally produce an ordered pattern. Not impossible, just spectacularly unlikely. It might happen once by chance, but traveling against the flow of time would require it to keep happening again and again, endlessly, as if the universe insisted on winning the lottery repeatedly. Boltzmann argued that the second law of thermodynamics, and by extension the arrow of time, was a statistical necessity. Disordered states are vastly more probable than ordered ones, even in a universe governed by symmetrical microscopic laws. Tragically, Boltzmann faced a barrage of criticism in his lifetime for his atomic vision of reality. He died by suicide before his ideas could be fully vindicated. Today, his work stands as a pillar of modern physics, and it leads to a surprising conclusion. If we visualize the universe as an immense billiard table, then the increasing entropy that defines time's arrow suggests we are still within sight of the beginning of the game. The universe must have started in a more ordered state if we are statistically moving toward randomness. But that feels counterintuitive. The early universe, often described as a smooth, uniform soup of protons and radiation, sounds more random than the structured cosmos we see today. Stars, galaxies, planets, humans, minds. How could a uniform universe have lower entropy than one filled with complex structures? Here's the twist. Human notions of order are not the same as entropy on a cosmic scale. Entropy can be calculated. We can estimate the entropy of the early universe and the present universe using Boltzmann's constant. At the Big Bang, the entropy of the compressed, radiation-filled baby universe was not low. It was about 10 to the 88th times Boltzmann's constant, a 1 followed by 88 zeros. Today, the entropy of the universe is around 10 to the 103rd times Boltzmann's constant, a 1 followed by 103 zeros. That's some quadrillion times higher. So yes, entropy increased, but the starting point was not the pristine low-entropy paradise we might imagine. It turns out the kinds of order we instinctively notice, like living organisms, cities, or galaxies, barely move the needle of cosmic entropy. 14 billion years has only modestly changed the entropy of the background radiation left over from the beginning. So what drove that enormous increase? One structure, above all: black holes. These dark objects, lurking at galactic centers and scattered elsewhere, are the result of vast amounts of matter packed into a small region. And because they contain so many particles, there are almost limitless ways those particles can be arranged while still creating the same massive, lightless hole in space-time.
That multiplicity of arrangements is entropy. It means black holes have staggeringly high entropy. In fact, the black hole at the center of the Milky Way alone has entropy roughly 1,000 times greater than the entire universe just after the Big Bang. Over time, gravity drives more black holes into existence and causes existing ones to grow, pushing the entropy of the cosmos higher and driving time's arrow forward relentlessly. But here's where the story becomes even more unsettling. That increase will not continue in the way you might assume forever. The so-called heat death of the universe is the idea that all energy will eventually become evenly distributed across near-infinite space. Entropy continues to rise as structures form and collapse, as black holes eat and merge, as the cosmos drifts toward equilibrium. But one day, trillions upon trillions of years from now, black holes will have swallowed the last particles in the universe, and then, due to a strange effect discovered by Hawking, they will evaporate away.
Nothing survives the end state where matter and usable energy are gone. When entropy has reached the maximum it can reach, the universe becomes a kind of white noise of randomness, ultimate equilibrium. And since time cannot flow backward, it will remain that way without change. Time itself ceases to have meaning. This, in one vision, is the true end of time, a cold, black, empty universe existing outside space-time as we know it. Yet it would be wrong to assume nothing happens in such an empty universe. Entropy at maximum does not mean a single frozen arrangement. It means there are near-infinite arrangements compatible with that maximum disorder, and the stuff of the universe can fluctuate through those random permutations. Equilibrium becomes dynamic. The universe may not become more ordered overall, but statistically, rare fluctuations can occur. Toss 100 coins, and it is extremely unlikely all will land tails. Yet it is not impossible. And if the universe at heat death is effectively eternal, then there is plenty of time for every coin toss, every permutation to happen eventually. This is where modern physicist Sean Carroll enters with a provocative origin story. Suppose a universe has lived its life and reached entropic equilibrium long ago. The result would be a timeless parent universe with random local fluctuations. One of those fluctuations might, by chance, configure energy into a highly compressed pocket with inexplicably low entropy. A baby universe. The billiard balls reset. The first break happens again. Carroll argues that this could be the beginning of a new Big Bang, our Big Bang, born as a hiccup inside a timeless parent. It's compelling. It fits with cyclical stories of death and rebirth, but it also opens a door to something deeply disturbing. Because if a timeless parent universe can randomly produce a baby cosmos, it can also randomly produce other things. And some of those things are far easier to produce than entire universes. A new universe is an enormous coin toss. It requires an extraordinary fluctuation, an absurdly rare configuration of energy and entropy. But producing smaller pockets of organization might require far fewer tosses. And this leads to a thought experiment that haunts modern cosmology, the Boltzmann brain. Named in honor of Boltzmann's statistical logic, a Boltzmann brain is, in the simplest terms, a bodiless human brain that spontaneously appears, fully formed, drifting alone in space, complete with thoughts, artificial sensations, and memories. The idea sounds insane. It sounds like science fiction pushed into parody, and in ordinary terms, it is vanishingly unlikely. But in a universe with eternal time and maximum entropy, vanishingly unlikely is not the same as impossible. Given enough time, even the most improbable permutation will occur. Given even more time, it will occur again and again. In purely statistical terms, Boltzmann brains become inevitable. Now comes the horror. Actual humans, complex bodies, planets, evolutions, societies might be vastly less likely than disembodied brains flickering into existence in a dead universe.
If that's true, then statistically, your current thoughts and experiences are more likely to be the illusion of a fictitious universe conjured by a Boltzmann brain than true reflections of a cosmos still young and structured. It follows that, under certain eternal equilibrium theories, the most probable observer is not a human in a living universe, but a lonely brain hallucinating reality in a dead one. Physicists do not believe this is what's happening, but the Boltzmann brain problem is like a warning flare. It tells us that a theory leading to eternal maximum entropy and endless time may be wrong, or incomplete, because it produces absurd predictions that threaten the credibility of our own existence. If we really are here, experiencing the universe at nearly 14 billion years old, then the idea that the universe will persist forever in timeless stasis must be wrong, or at least not the whole story. Modern cosmology must find a theory that avoids an eternal equilibrium long enough for Boltzmann brains to outnumber real observers. We need a definitive end to spacetime, or a cosmic mechanism that prevents endless permutations. And there are possibilities being actively pursued at the bleeding edge of theoretical physics.
A contracting universe leading to a big crunch and rebirth. Exotic scenarios in string theory. Vacuum decay events that end the universe abruptly. Models where inflation creates a multiverse, yet our local spacetime ends. The search continues, not only for understanding, but, strangely, for the sake of reality itself. And so Augustine could not have known how close his meditations were to modern physics. He wrote that time evades definition, and he was right. Eddington described the arrow of time, but could not fully explain why it exists. Boltzmann, in his troubled brilliance, offered a statistical account that still leaves open terrifying consequences. And even now, modern physicists have no definitive explanation for the beginning or end of time. Which raises a grim thought. Perhaps all these influential minds, Augustine in his window, Eddington with his feathers, Boltzmann pacing across Europe, were no more than minds floating through space, dreaming of a universe they could almost understand. More disturbing still, perhaps our memory of these scholars is itself a fiction, fabricated by a single Boltzmann brain drifting in an eternal, timeless universe. Or perhaps, sometime sooner, theoretical physics will finally find the answers we seek. For the sake of our reality, we can only hope that it does. You've been watching the entire history of the universe. So, what are your thoughts on today's topic? Make sure to like this video and subscribe to our channel HaiAstro so you won't miss any of our upcoming posts. Thanks for tuning in. See you next time.